Hello, everybody. I'm Nadiva Saikar. I'm a volunteer with Mars Society. So today we have Mr. Wilson Hago. He's going to speak on the topic, a thermochemical approach to convert CO2 and H2O to sugars. So we'll get started.
Great. Thank you very much, everybody. It's a pleasure to be here. This is my first time I've given a talk in front of the Mars Society. Actually, I consider myself a neophyte in regards to Martian matters. But today I'd like to tell you about the approach that we took in converting carbon dioxide and water to sugars in regards to the bidding the fulfillment of the NASA CO2 Conversion Challenge prize. So I will say that it's an important topic to talk about because for future Martian inhabitants, the generation of sugars from in situ resources is going to be an important task to achieve on a massive scale. And so NASA and others have seen to it that there are multiple solutions to this problem that can be implemented on a big scale. And so today I'm going to be talking about one of those solutions and how it can work as something viable or at least something to consider going forward. So first I want to start by acknowledging our team that worked on this in various parts. Randy did experimental work. He's got a PhD from chemistry from UCSB. Sally Delul did some of the early work, experimental work. Alan helped us out in various things with when the judges were here. Jesse did a lot of the background research in this area. So very proud of what we were able to achieve. And what I want to say is that we started in this journey not looking at Mars and solving Martian problems. We started this journey looking at what we can do to solve problems here on Earth. And a major problem in the world right now is just that there is an excess carbon dioxide in the Earth's atmosphere. As you can see here, here's a graph of carbon dioxide concentrations as a function of time since the 60s as measured at the Mauna Loa Observatory. You can see that there's a relentless drive in the CO2 concentration, and this is due to the emissions coming from anthropogenic emissions. And so our main line of business is basically addressing this problem. Is that there's way too much carbon dioxide here on planet Earth. So for us, the question or the mission is, what can we do in order to bring this curve down? And so we've been looking at various approaches to do so. But along the way, we encountered this problem of okay, well, how do we do sugars on Mars? And that's kind of it was a fun diversion for us. So here in this graph is showing actually the how bad the problem is for the past several 100,000 years, and actually for the past millions of years, we have not had levels of carbon dioxide that we're seeing right now. And this, as I mentioned, is due to anthropogenic emissions, and we want to be able to reverse the massive amount that you see at present age to something that has been traditionally found around, that something where humanity is accustomed to living with. So looking at this problem, right, we see that the atmosphere on Mars is kind of peculiar from that on Earth. Is that the atmospheric pressure at the beginning, at the outset, it's a very thin atmosphere. You find 6 to 7 millibars compared to over a little bit over 1,000 millibars here on planet Earth. The Martian atmosphere is 95% carbon dioxide, so you have this abundant resource of carbon there. There's lots of water at the poles. There's water on certain areas, and we have experts in water. And thank you for the previous speaker on telling us where to find water on Mars. And there's a little bit of oxygen, which is kind of a puzzle to some people, just because just typically you don't find that oxygen. Usually you find the oxygen bound. A little bit of carbon monoxide and just trace amounts of water. Here we have citing a figure of 210 ppm. for the water, and then you also find a hydrogen, deuterium, oxygen is deuterated water, or half deuterated water, I should say. Some xenon and krypton, and so that's the interesting thing, is that you already have the raw materials to make carbohydrates on Mars. I mean, for just starting with carbon dioxide and water, you can make a wide variety of hydrocarbons. That being the case, basically, you have the basic materials to make plastics and to make a whole bunch of things, basically the infrastructure that we are accustomed to at Earth. So NASA came out with this challenge, put it out in the world, starting in 2018. Basically, okay, how do we convert carbon dioxide and water to sugars? And particularly, they were focused on glucose. And then this contest began in 2018. It ended in May 2019, and it offers a phase 1 participants. It offered a prize of $50,000 to each team that won. We were not participants in that prize. I didn't know about it, actually. So luckily, I mean, there was another phase to this prize, a bigger phase, which began in September 2019, and which anybody could enter. And then basically this involved not just a proof of or a written proposal, but this actually involved coming up with a solution that can be implemented in the lab. And so there was a period for the eligibility verification, and then there's a progress midpoint reports. Eventually, I mean, we had people that submitted and had a talk to convince judges that the solution was viable. And after doing that, there was a site visits, people actually coming to our lab to inspect whether the solution make any sense. And then the winners were announced in a couple of months ago, August 2021. We were one of 3 winners in this contest, and that's why I'm here for you, trying to tell you how we did it. I feel a responsibility to do so because this is taxpayer money, and I want to just tell you that it was well spent. So our initial approach to this in this contest, when we got into this thing, was basically to decompose carbon dioxide into carbon monoxide and oxygen. And this is something that we kind of decided, but looking at the literature, it's decided that it could be done by using microwaves. But it turned out that NASA already figured this out with a machine called MOXIE. Instead of using microwaves, they use a electrolysis approach to doing so. So we said, okay, we're going to generate break down CO2 into carbon monoxide. We're going to break water with electrolysis, and then we're going to combine the water and the hydrogen with the carbon monoxide to make methanol. This is standard reaction. And then the methanol is going to be reacted with oxygen, another well-known reaction, to make formaldehyde. And the formaldehyde, then it's going to go, it's going to use a 100-year-old reaction called the FORMOSE reaction to create a variety of sugars. And then once we get the sugars, then we can just separate the sugars and use a chromatography column to get declosed, just using the right column. So that was a challenge that we set out at the beginning. We figured out, okay, using various numbers from the literature, that we could expect certain conversion rates from each of these steps. Ultimately, we figured out that we expected to get an overall conversion rate of about 4% in terms of the sugar, in terms of what's the initial carbon going in and what's the output carbon going out. So that was expectation going forward. In the end, we found out one of the requirements of the contest was that you had to do this in a 7-hour period. We just didn't have the time to do it within the 7-hour period. Plus, it took too many steps. So we had to modify the approach so that we do it in fewer steps. And look, and this is kind of demonstrates what we actually did. We combined carbon dioxide directly in concentrated form with hydrogen from either an electrolyzer or a compressed tank. We sent it to a compressor, which sent it to a methanol synthesis reactor. And I'll show you a little picture of that. which then the methanol synthesis reactor, once it makes methanol and water in gas form, condenses it, and then sends it to a formaldehyde synthesis reactor. The formaldehyde synthesis reactor, then the formaldehyde is reacted in a carbohydrate reactor to yield the sugar products. So that's kind of the basics of the whole approach. Now, want to say a little bit about the what it takes to capture carbon dioxide on Mars. It's not any more different than what's been doing right now by various teams in order to implement this on a massive scale. It's called direct air capture. There are various approaches to doing so. You can use mechanical pumps. You can use something called microchannel adsorption or cryogenic separation. Cryogenic separation means basically if you're operating in a region that's cold enough, you can just, the CO2 drops out and it drops out, it becomes solid at -23 Celsius. So there are regions where you can do this. The microchannel adsorption is probably the best thing to do that because there are several companies such as Carbon Engineering, Global Thermostat are doing this. Basically use a zeolite type of adsorbent, and then you have repeated cycles of adsorption and desorption of the carbon dioxide. So you're able to extract the carbon dioxide from the Martian atmosphere and have it deliver it in concentrated form to another process. On the left here, I'm showing kind of a picture that was a setup that was done by the Pacific National Laboratory. And it shows a zeolite called 13X. Works pretty well in terms of capturing the carbon dioxide. So it's not a problem. The next step is for us was the methanol synthesis reaction, and then this step, I should say, is widely practiced on planet Earth. Basically, once you have the methanol, you can go ahead and make a variety of different derivatives that are widely used in the industry. Actually, methanol here on Earth is a $50 billion industry. Once you get the various derivatives, you can convert them to a variety of different products shown here: gasoline additives, olefins for plastics, and then so this is used. These products are used in a variety of different sectors. I mean, automotives, you name it. And then, so the flexibility approach is that you're able to basically use methanol as the keystone for the chemical industry on Mars, and that's kind of crucial because you want to be able to generate all of these things ultimately on Mars and have a vibrant industry with being able to make products from just carbon dioxide and water. Okay, and then so this is kind of the approach. Our line of work is basically starting with biomass and going through a process creating the syngas and then making the methanol and then making higher value products. Right now, what we're trying to do is to stay away from using fossil fuels to make the syngas and make these higher value products. Ultimately, you want to use solar and wind power and just capture the carbon dioxide from the atmosphere and just go this route, right? So that you just using in situ resources, CO2 and water. So the basics. Let me move this out of the way here. Initially we started out thinking, okay, this is the main reaction that we need to do: CO plus 2H2 going to the methanol. It turns out you can just use this just as well. Avoid kind of the middle step of the CO2 decomposition, and then just mix the carbon dioxide with 3 moles of hydrogen to create the methanol, and that just works as well. You just have to vary the experimental conditions just a little bit for what's originally practiced in industry. Another reaction that happens frequently in these things is the water gas shift reaction. We generate when the CO and the presence of water gives you CO2 and hydrogen. So this shows the methanol equilibrium concentrations that you expect, and so what this shows basically is that this reaction is most favorable at low temperatures. By low, I mean I'm talking about 200 Celsius, and then there's a different optimal mixture of CO2. But what is interesting is that in the process of making the CO2, you just put in the CO2 into the reaction, you form CO in situ, so you don't have to put the CO on the outside. It's just it forms itself in the reactor. So that's why this thing works the way it does. So that's to our surprise, at least, you can do this reaction with just working with CO2 and hydrogen. And this is a view of our apparatus that we used. This is the compressor, which basically we were operating about 80 bars and 200 Celsius to make the methanol, and the methanol is made in this reactor. It has the catalyst that does the conversion, and then once you have the methanol and the water, this condenses in this thing, and then you just open up the valve here, and out comes liquid, a mixture, 50-50 mixture of methanol and water. So so that's that magic of gas to liquids, which you actually demonstrate. And then here you see using a gas chromatogram, the output trace of what we collected, the liquid that we collected. Here's the picture of the liquid. It should be clear, but there's a little bit of metal contaminants in it. And ultimately, as I mentioned, this is a big industry on Earth. This is a picture of a large methanol plant in the Arctic in Russia, but it looks like it's something that you could just transplant on Earth. Never mind the blue background, but it's it's very scalable. That's my point. Okay, and the next step was to convert the methanol to formaldehyde. And then the good thing about our approach is we didn't have to do any separation. I mean, once we just put the water, the methanol water mixture, and then just feed it directly to the methanol to the formaldehyde reactor. The basics, it turned out the basic reactions that we're able to accomplish this is just basically using the methanol to form formaldehyde and a little bit of and hydrogen using a polycrystalline silver catalyst. And the conversion was at 50% at 650 Celsius. And this should be a fairly stable catalyst. I mean, we're talking about months and months of operation before we need to do something about just regenerating the catalyst. Here's the input trace where you see this big peak over here is the methanol. There's a little bit of formaldehyde from the previous run. And then on the output trace, you see that you formed a lot of the formaldehyde, and then you have much less methanol. So this reaction works fairly well. So once you have the formaldehyde, then you go on to the FORMOSE reaction. As I mentioned, this reaction is a 100 years old reaction, and then the basics of it is that under basic conditions, formaldehyde, the nucleophile attacks the carbon and the formaldehyde. It creates this entity, which then couples, does a carbon-carbon coupling, which creates a glycerolaldehyde. And this is kind of the basics for creating further, adding more carbons to this, because then this thing can also undergo nucleophilic attack, and then you just form something like 3 carbons, 4, 5, and 6. And then this on the right, I'm showing how basically 3 molecules of glyceraldehyde can form and combine it to form a sugar. So the trick is just to be able to do this and do this so that in a reasonable amount of time, and be able to demonstrate kind of that this is sugar. So this is the basics of the FORMOSE reaction. There was a paper not long ago by Delidovich and others looking at how the formaldehyde reacts under the presence of different initiators. So they tried glycoaldehyde, hydroacetone, fructose, and even glucose. And that's interesting is that glucose itself as an initiator, it is an initiator that basically allows the reaction to be autocatalytic. So if you have a little bit of glucose, the reaction, it generates more glucose. So ultimately, if you can find some way of just either whatever initiator you use, and then you form glucose, then that's it, the game is over, right? Because then you can use whatever glucose you form for further reactions on the road, and you don't have to depend on bringing any more stuff. There was a paper in the 1980s on the right here showing that basically as a function of temperature, that as you increase the temperature closer to the boiling point of water, that you find there's a preference for making C6 sugars. Ultimately, this is what we need. That's what worked for us. The stuff on the left did not work so much for us. The stuff on the right did, and this is more of the operating conditions that we use in order to generate the glucose and other sugars. See, how am I doing on time? 5 minutes. Okay, so so the FORMOSE reaction is fairly straightforward. Once you have the right operation conditions, you add your base, you have the formaldehyde in there, then you just the reaction changes quickly. I should say, go back to this previous one. These guys over here did not use any initiator, so this is in contradiction to what these guys were saying. And this, although we did use initiator in our reaction, I think ultimately there's probably no initiator needed to get this going. So this is what the reaction looks like. I mean, the reaction changes from colorless once you get going to a beautiful brownish color. It starts a pale yellow and turns into kind of this color, slightly brownish color. It smells like you have sugars in there. So we sent the analysis of this thing to the lab because we want to do our own verification of this, and we found that there was glucose, a bunch of other sugars, fructose, lactose, sucrose, maltose, and this is only the stuff that they were able to pick up with their method. This was a ion chromatography method that they used to pick up to identify the sugars. When the NASA team was actually, it consisted, here you have a picture of us making the product and shipping it, because we had to ship it. They had given us a special container to ship it, and here is a picture of us. This is Janice Rudermeyer from NASA. She's working for Axiom right now. They're working on the space station. And then, so we just kind of showing us that we are shipping product to them for their own verification. We almost missed the bus because it was kind of towards the end of the day. Missed the FedEx truck. Luckily, Alan ran after it, and then we're able to meet the requirements. Should say, in terms of other winning approaches, the other team that won was the UC Berkeley team. They made glycoaldehyde electrolysis using copper as a catalyst. This is as far as I can understand. It may be not entirely true, but this is what I've been able just to from reading trying to understand what they did. They've made formaldehyde just from CO2 and water in a beaker, basically using electrolysis, and then they use the FORMOSE reaction like we did to make the formaldehyde. There was the air company team in Brooklyn that basically they combined the CO2 and water to make alcohols and then two aldehydes, and then they use a modified FORMOSE reaction to get product. So at the end of the day, I mean, it's just like, how did you generate CO2 from water? You have to depend. All three teams depended on the FORMOSE reaction, 100-years-old reaction, and not much improvement from then. But that's the way that it was done. And then so there may be other ways in the future to find a better way, but we could not find an improvement over that. So that's the kind of the end of what I have to show to you today. So thank you very much for your attention. Be happy to take any questions. Let me stop sharing. I can't hear anybody.
Okay. So hello, Wilson. Yeah. So one question we have here is, how much energy does the reaction require?
Which reaction? Because there were several reactions.
Oh, that is, that's all the question says. So.
Yeah. Okay. The methanol reaction is it's an exothermic. So all of them require actually the methanol reaction is exothermic, right? So the hard part is just generating the hydrogen. So that's a very energetic. It requires a lot of energy, and then also the formaldehyde reaction, and then I don't think, as I mentioned, the FORMOSE reaction is just you just heat it up, and so it doesn't. You don't have to heat it up a lot to get it going.
Okay, and then another question is, how efficient is it compared to plants?
Plants. This is not. Plants are more, I guess, on a more efficient. Well, actually, I should say the this is actually more efficient on a carbon basis, because in the end we were able to find it's about 3.7 or so percent. Actually, the kind of the numbers that we expected from the beginning, but using a different route. And so we have to put in more energy, but in terms of efficiency, at the end of the day, this is more efficient process. But ideally, I mean, you may want to still use plants on Mars, right? This is just kind of would be something to kickstart the whole process.
And then another question is, what rates of production were you able to get, in what quantities and what time?
Right. So we were able, at the end of the 7 period, we were a 7-hour period, I should say. We started out, as I mentioned, you have to talk more in terms of efficiencies. We're on a carbon basis, we're able to generate, as I mentioned, close to 4%. So it depends ultimately on kind of what then the initial amounts. If you start with a lot amount, you're going to generate a lot of material. But for us, we're able to generate stuff in the milligram range during the 7-hour period, given our experimental setup, which you have seen.
Okay. Could some form of gas diffusion process harvest the already occurring CO in the Mars atmosphere to bypass the initial CO2 to CO step?
Yeah. Can you say that again? Because I'm not.
Okay. Yeah. Could some form of gas diffusion process harvest the already occurring CO in the Mars atmosphere to bypass the initial CO2 to CO step?
Yeah, I don't know of any. In principle, it should be. I mean, there's a lot of metal organic frameworks that are size exclusive and just have the right size to do so. But I can't tell you right off the bat what it is.
Yeah, and one person wrote more of a comment than a question. It's great to see that all the teams came up with the FORMOSE reaction.
Mm-hmm. Yeah, I mean, I guess you can say it's great. You converge on the same answer. And the other hand, I mean, well, I just go back and say the FORMOSE reaction, people are very interested in it because it represents basically, people think it's the origin of life equation, or the way life started on Earth, right? You have formaldehyde either coming in from outside the planet, and then you have a way of this in condensing in basic environments, and then ultimately you form sugars. And so you can imagine this being the formaldehyde in some sort of hot bath, and it's forming sugars. And so this is and maybe there is no other way that nature found, or in the hundreds of millions of years, that to be able to form sugars except through this method. And that's why it was the only way that three teams were able to converge. But that's the speculation.
Yeah, so that's all the questions that we have, and we have 2 minutes till the next workshop starts.
Okay, well, thank you very much.
Yeah, thanks for your talk.